Hello Internet, welcome to part 2 where we actually show how can we build a dependency injection system. In the previous part we've shown that FastAPI has like a super nice and clean API for supporting dependency injection, and we've shown that if we model our types correctly with some kind of like black magic of Python with annotated types and with this depends magic class of FastAPI, we get our database connection inserted into our route without us needing to think about it very much. And that was quite nice. We've curled our server and we got some result from the database, which is awesome. And now in this part, we're going to drop FastAPI completely, and we're gonna directly work and develop our own small dependency injection solution. Maybe let's see if we can actually model it correctly and have it work. Let's say we have some kind of function and we know that we have some kind of parameter. We need to say this depends on something. So we're going to go with the same ergonomics of FastAPI, and that means we're going to use annotated types, and here we're going to inject our dependencies. So we're going to say this depends on something, some other func. And hopefully, if we'll say if a would be an int, that would be wonderful. And the only thing that FastAPI has that we do not have is that they have a decorator that enables this injection. So this is our only thing that we're going to have to do that FastAPI does not have to do specifically for that, and that the root of our dependency tree needs to have this some kind of injectable decorator that FastAPI does not have to do because they already have their own decorator. So let's try to model this. So we have our class depends, and what we'd like to say is something in the lines of this needs to be a callable and can be actually a sequence of anything. It can be a sequence of other dependable objects. So we do have something like that. And we'll try to model it like very carefully and slowly. So for this moment, let's just save this function in this keyword, and let's think about our injectable decorator. So what we'd like to have here is func tools, wraps, func, diff, wrapper, and we're going to modify the signature because we're going to inject more args here. So at this point, we need to resolve let's call that dependencies. And how do we infer the dependencies themselves? We need to, let's say, infer, and we'd like to introspect the type annotations. So let's go with annotations. Let's see what we have here. So I think we're going to match. Hello, this is Sue from the editing room. Apparently I wasted like 10 minutes looking up documentation. So I'm gonna save you all the trouble of me going through that, and we're gonna just cut to the next part where it's solved. If you'd like, comment and like ask me to upload it, and you'll get an unlisted video of me wasting time. Back to the video. We now have a list of all our annotations. Inside of them, every time our metadata is a depends object, then we can have that as a dependency. And dependency takes no arguments. We need to actually model that ourselves. We may want to. So let's have like a data class, and this data class will have a callable, and we'll now type it as any, and then we'll fix our typings later. And this of course will be completely frozen, and we can actually have that as a list comprehension because now we know everything. So this will be a dependency of annotation metadata. No, actually, let's keep it this way. If this has more than one type annotation, then we don't know what to do with it. So we need to have some kind of assertion and say we're only going to take the first one, or do we error out if people like do crazy things? I think we're gonna want to error out. Oh, actually, this is a dictionary. This won't be a list because we need to resolve them as a tree. So this is going to be a dependency. Yeah, this is way more like what we'd expect. And this is going to be a mapping from string to dependency. And let's return our dependencies. Now, what we also need to do is introspect into every callable thing that is in here, because this function actually can have its own tree of dependencies. So let's solve that one. So we can say now this is a sub dependency. Yeah, and we can update. We need to merge them safely somehow. and then solve everything. We need to meditate on this one. Let's keep here a to-do of how to handle sub-dependencies correctly. Let's start with just having a flat dependency tree, which is not a tree. It's just a dictionary. But let's see. We have now our dependencies, and if we print them, we get a dictionary with a dependency, function, other function. That's awesome. So I think we don't need to actually have this depends and as like another class. We can just literally use this one, metadata. It's already in the correct form. So we need depends. We do not need this one. And this is a data class. And this is a func, which is a callable. This can only take depends things, I understand. And we need our from future import annotations friend. And this needs to be some kind of type var. So we have our small dependency tree. Now we need to solve it. So let's call that solve dependencies. And we know we need to do something like, well, name dependency func or func dependency. That looks like the correct solution when we're talking about, well, possible callees depends something. Well, that's not true. This should be a partial. So this is a dictionary of callables with 0 args and some kind of return value. That is true. This is callable to tease. Cool. So I believe what we'd like to actually do is solve our dependencies here somehow on construction time of the depends keyword, because everything that has the depends keyword we can already pre-solve. That might actually be a really nice way of handling nesting things. So how we'd like to do that? Def post init, I think that's called. So let's try to introspect what happens here. We have our function, and first of all, I'm not gonna handle the not callable thing right now. Let's just say that we have our annotations, which is typing get type hence include extras, and we can actually use the same infer dependencies here. We don't need to. So this thing is actually can be reused and definitely can. So what we'd like to do here now is to basically have patch our function. We'd like to use something like functools partial and patch in our dependencies if we can solve them. That means that we can have self func now as a function that basically, it is frozen. That is true. Can we verify that or something? Let's say field from data class. And what we'd like to do is something like, first of all, validate. Actually, this is our own class. We can do whatever. Let's just not use that data classes. Let's just do this def dunder init and have our func callable t. And let's not actually save it. Let's first of all have our deps be inferred, and then functools partial, and then we inject our own dependencies. And that's how we solve the nestedness, this nested function. Okay, I have somewhere a func that's a func. So what do we have here? We have a depends class that does a little bit of magic because it introspects into our type annotations, and once they are so we look into all the annotations, we look only for the depends keyword, and everywhere that we have a depends thing, we know we need to solve this in a nested way. And that's already happened because we've initialized this. So we are only looking for the initialized depends things. I'm not sure this would actually work as I expected to. Maybe we should write some tests. So here we have already injected the one, which is nice. And that means that we actually look at what f does here. It is missing one positional argument, a. Interesting. Oh, this won't work. We have our dependencies, and we should have injected them right here. Amazing. So this is recall, and then we can inject our own equals something if we'd like right here, and that should work, I believe. Let's print e here, and this actually works. So we have our own nested dependency, not nested yet. Let's see if we can actually have this properly nested. But for not nested not nested dependencies, this actually works. This injects the correct thing in time, which is quite nice. And we might want to actually, so we don't want to call this function yet, because this can actually change between the time that we define the function and the time that we actually want to use it. So we need to solve this dependency in real time. So this is solved as in we have our function pointer, but we don't want to actually run it yet. So we have our dependencies. What we'd like to do is here in the wrapper is say solve. Solved is a dictionary comprehension of this function iterated over time, and then we inject the solved. Okay, so this should work, and this would actually change now if we have our dependency be something like UUID. This would work, yeah, and the assertion would fail because I forgot to update what we're expecting here. And now if we call this function twice, we'd actually have different IDs every time because we're solving the dependency in real time and not before, which is quite useful. We have to use our injectable thing here because we don't have A assigned here, and this actually like patches the first node of the tree. And after that, every sub-dependencies that we have here we should be able to solve without this injectable decorator. As you can see, all the injectable does is basically it infers the dependencies just like our depends does, and then returns a partial function with these patched arguments. So let's try to write our sub-dependencies. So let's write foo, which has bar, which is an annotated string, which is itself ends on a lambda bar. Sure. And this, we'd like to return this thing, and let's depend on this one. So we should be depending on foo, and now we don't need to pass any arguments because they should basically just work. And we see that we have fucked up something. Let's try to debug what went wrong. So this would be a string because this returns a string, and let's try to have that chain of functions basically patched all the way. So first of all, let's define some bar keyword that just returns bar, and this is depends on bar. So foo depends on bar, and this is just a string, and we have not solved anything. We just cleaned up some stuff. I really want to get that formatter thing working, but never mind. Let's proceed. So this depends right now is, let's try to look at it from this perspective. So we have an object here that's called depends, and it's getting a function, a reference to a function. And this is what we're having here. This one does not have any dependencies, so this is going to be an empty dictionary in this sense. If we try to print self, func, and deps, we'd see that if we go for this depends object that depends on bar, we're going to have an empty dependency array. So we have our partial, and that means this function is already fulfilled with all it said keyword arguments. It should be called correctly. We have that function. And now let's try to let's print, where is it? Right here. Let's print it. Let's only print self func. This is actually going to be a little bit more clean, maybe. So what do we have here? We have a partial function of bar with no dependencies. That's great. And foo has one dependency. It's actually, let's see, it's a partial function foo with bar as its depends object, and the dependency of bar, which is a depends object. So this is where we have basically failed. What we need to patch in is that if this function is a depends, we need to actually use the function here. Not this would be a callable. We can actually remove this and ignore, let the type checker work for us. And now it's saying that it's missing a required positional argument. So let's try to patch that thing. Let's see. Injectable, infer dependencies, get type hints, eval type, infer dependencies. So we have in our nested dependencies, we have something here that's not working as we'd expect. And that is here in our first depends call. Let's see. We have our injectable, and we're trying to pass it this function. Is this function already initialized? At the time of this decorator, it says eval forward code. So we can actually have that only happen at runtime. That's interesting. I'm not sure if this is a good thing or a bad thing. Probably a bad thing, but we can live with that. So apparently we cannot use partial here because this does not work. Or maybe since it's a partial thing, we can maybe have use the actual, if this is a functools partial, this is a class, this is a class. We have a way to access the original function, self func. Yeah, yeah, this is a function. So we now know that we can just infer the subdependencies of func. That looks better. So let's see what we have here. So other func does not have any dependencies. That is true. It depends on nothing. It accepts 0 arguments. Then bar has no arguments itself. And then foo depends on bar, which is a partial function with bar already pre-filled. Is that true? So it's just waiting to be invoked, I should hope. Then we need to somehow like solve this dependency tree, because right now we're still not solving it, right? We have A here, which works, and B, so this assertion would obviously go, and we can actually debug that. We'll see that B, if we just call it, would return that bar thing. So how come we haven't called it? So we infer the dependencies, we have created this bar, we have it saved the function, and in this injection time, what we should have done is basically resolve it until it's not callable anymore. That's not true. Like we need to recurse into this. So this should be actually, well, this should be recursive. So let's define that recursion. So let's go. We have the solve, and we give this a dictionary of string to callables, or, well, could recurse. And if it's a depends, then we solve again. And we actually don't need, let's actually keep this simple. This should be just a dictionary. Is it? No, this should be, how do we know to stop solving? Where to stop solving? Let's try to think about it for a minute. I would have wanted that this function call would actually just do the thing, do the right thing. So maybe this is actually somewhere here in the definition of the dependency. We have our dependencies, which themselves are nested. Then this, I'm truly not sure how to handle this correctly. We need to know where to stop. This is probably like an obvious graph tree traversal thing that I'm just now blanking on. But let's try to print our way to success. So we have a tree of 2 nodes. We have 2 nodes on the first level. We have a partial method, and then we have a partial method that has an argument, which is a partial method, which is not what we'd want. We'd want something that when we call this partial one, it would just go all the way down, and we'd just solve all the subtrees. So that means that we don't want to call the dependency and just have it do the thing. We need this to be like a solution. So let's try to formalize this as an actual solution. So we have our depends, and let's actually define this as def solve t. And this would mean that we have here self deps, and we still don't want to solve them like this. So let's just have this function right here. And this is not a partial, this is the actual callable of something to t. And we'd like to say something like dependency solve. And this would have to be, well, a depends dictionary, because we have to have that recursive solution thing. So let's infer these dependencies and have them. And this actually is not needed anymore, I believe. We just have our depends, and once they are inferred, we are good to go. So this one would solve recursively. We just go one level deeper every time, and that means that every root dependency would just work magically, maybe. And we have our bar resolved correctly, and we have, I think, a working dependency injection library. So maybe let's write some tests and see that actually working. So let's go with def test lat deps, and we have here def foo, which returns a string, and we have bar, which returns a string, and we'd like some baz that depends on foo and bar and returns this one. And we can assert that baz equals foo bar, and this needs to be injectable. So let's see if this assert actually works. And we have arguments, missing positional arguments. Well, that sucks. Let's see what we have. Where have I fucked up? So of course, this has to not work now that we're testing it, but this is a good thing, because now we can actually try to debug correctly and have well-structured and tested code. So let's put our code right here, our test right there, and let's try to debug. This is getting a little bit out of hand, so let's try. So in here we have an injectable baz. So that would lead us to here, and we need to infer our dependencies, and we print them. Do I see any dependencies? I do not. So first of all, let's try to import these like from Z import injectable and depends. And the fact that we see an empty dependency array, that dependency tree, that's not good. That means this does not work. Our inference of depends is not what we expect it to be. Ooh, that is actually true because we're not using it correctly. This should be an annotated string. Yeah. Okay, so this is truly my bad. It depends on foo, and this depends on bar. And we have still some errors. And it's saying calling test flat depths, return none, not a test. Cert. So why do we have a return none? Calling function, return none, not a test. That's weird. It's sweet. That's really bizarre. Let's try to run that directly here. Let's just go with test. Okay, so I think we have some kind of problems with our test runner here in PyCharm. So let's just default to actually running this where we know things are working. And this just let's just make sure it says test API. Let's go with like something more verbose, flat depth, and let's just make sure this actually fails if we fail it. And it says division by 0. So okay, we have a source of truth for actually running tests now. And we support this annotation type, and this actually works with some dependencies. And let's test nested depths. And we have bar, which depends on bar, and we have foo, which depends on foo, bar, which depends on foo. And this should be foo bar baz. That's an actual good test. And verbose, yeah, we just need a root which is injectable, and then everything else is solved recursively through this depends object. And hopefully you've learned something new about this today. I might polish this and actually publish this package on PyPy. But before that happens, we need to actually solve the other use case, which is quite interesting, which is supporting async dependencies, which are actually the most important and interesting thing here. But now that we have our tree solver, then this all other things should be quite easy to implement. Hope you learned something. I hope you enjoyed it, and I'll see you in the next video. Bye-bye.